Hi everyone, welcome to Deep Learning Fundamentals. This course will take you from basic building blocks of PyTorch to creating your own neural networks. So in the first phase, we focus on the core concepts that form the foundation of all of the deep learning models. So in this lecture, we're going to be covering PyTorch tensors, automatic differentiation, neural network construction, and the complete training process. So these concepts are critical to understanding more sophisticated architecture like CNN and RNN, and most recently the transformer-based models. So first, let's get into PyTorch. So PyTorch um, is the most famous, most widely used um, Py, Python library that is relevant for deep learning. So before PyTorch, Google actually came up with TensorFlows, but recently it looks like Google is abandoning TensorFlows, and more people are moving towards PyTorch. So it's kind of like something you have to learn in deep learning. So let's start with tensors. So tensor is the building blocks in PyTorch. It is the fundamental data structure in PyTorch. So tensors are multidimensional arrays similar to NumPy arrays. So if you have experience in NumPy, then it will be easier for you to work with tensors in PyTorch. So tensors are basically multidimensional arrays similar to NumPy arrays, but with added superpower for deep learning. So these superpowers include GPU acceleration, um, which dramatically speed up computation, automatic differentiation, which we'll discuss soon, and its deep integration with neural network operations. So GPU acceleration part is what they're talking about every day. So the reason why the NVIDIA stock is so high is because they sell GPUs, and GPU is something every machine learning, every deep learning model needs to train and for inference as well. So first we're gonna go through this code example, and in this code example you can see how to create tensors in different ways. So in the first way, we can create tensors using specific explicit values. So we can say, okay, create a tensor that looks like this. Or we can create tensors of zeros with a specific shape, or we can generate random values from a normal distribution. And we can easily move tensors to GPU with the .CUDA method, assuming you have compatible GPU available. And for those of you who don't have GPU available, you can always experiment with the Google Colab or other online cloud computing options. So bottom part shows the basic operations like element-wise addition and matrix multiplication. So these operations retain the gradient history when needed, which is crucial for training neural networks. So tensors are the fundamental of everything we'll do in deep learning. So becoming comfortable in manipulating tensors is very important. So we also need to talk about automatic differentiation. A key feature that makes PyTorch so powerful is its automatic differentiation system called AutoGrad. In calculus, we compute derivatives to understand how changing an input affects the output. Because basically, if we change the input by this much, then it will change the output by that much. In neural networks, we need to know how changing each weight affects the final loss or error. Without AutoGrad, we have to manually derive and implement the derivative function for every operation in our neural network. And that will be very tedious and error prone. And PyTorch's AutoGrad system solves this by automatically tracking operations and computing gradients. So in this example, we can see that we can create tensors with required gradients being true. So this will tell PyTorch to track operations performed on these tensors. We perform a calculation to compute z being x squared plus y cubed, and then call z dot backward on the result. So in this case, this will automatically compute the gradients dz of dx and dz divided by dy, which are stored in the dot grad attribute of each input tensor. So these are, so I pronounced this terribly. So these are actually the partial derivatives of z with respect to x and y. So this capability is what enables neural networks to learn from data. It is how the neural network determines how to adjust the parameters to reduce the errors. So next, we're going to talk about how to build neural networks. So uh, basically, we're going to use PyTorch's NN module. So NN stands for neural networks. So now that we understand tensors and the automatic differentiation, we need to see how PyTorch helps us build neural networks using the NN module. So the new NN module is the base class for all neural network modules in PyTorch. So what makes this module powerful is its modularity. So everything is wrapped up nicely, and it provides many built-in layer types, such as the linear layer, which is a fully connected layer, a convolutional layer for images, and LSTM for sequences, and more. In this example, we have defined a simple neural network with 3 fully connected layers. So basically, a fully connected layer is just like a matrix multiplication on the inputs. So the class inherits from the neural network module, and then it implements 2 key methods: the init method and the forward method. The init method defines the layers and the components of the network. So basically, it's saying that, okay, we're going to use 3 fully connected layers. So the first one has these dimensions, the second one has these dimensions, and the last one has these dimensions. And the forward method defines how data flows through these layers. So this network has 10 input features. So which explains why the first linear layer is of the dimensionality 10 times 50. And the hidden layer has 50 neurons, and another hidden layer has 20 neurons, and finally it outputs 2 values. The value activation function introduces nonlinearity, which allows the network to learn complex patterns. So in the does it provide value? So yeah, here this is the value. So every time you feed the data through a fully connected layer, you apply the value activation function. So this introduces additional nonlinearity and allows the network to learn more complex patterns. So if you don't apply such nonlinearity to the model, then what you end up with is basically a bunch of matrices multiplied by each other, and then it's just gonna be a very complex matrix multiplication. So to improve the learning ability of the model, it is adding the activation function after every fully connected layer. So this organizational structure makes PyTorch code very clean and intuitive while building even very complex architectures. So this is a very simple idea, and as you see that as the example gets more and more complicated, it will kind of always follow this basic structure, which inherits from the NN module, the neural network module. And then we're gonna talk about a training loop. So with our neural network defined, we need to understand how to train it. So basically, the neural network that we defined by inheriting from the NN module is specifying the forward process. It's specifying the structure of the forward process and how many parameters and what type of parameters are there. But it doesn't tell us how can we twist those parameters for training. So the training process in PyTorch follows a standard pattern called a training loop. So every training loop consists of four essential steps. For first, we got a forward pass. So in this step, we need to run input data through the network to get the current best predictions. And the second step is loss calculation. So we need to measure how far these predictions are from the true targets, the ground truth. And the third step is backward pass, or it is called back propagation. So in this step, we're computing the gradients to determine how to adjust the weights. And in the last step, we have the optimization step, where we actually update the weights using these gradients to improve future predictions. So this is the overall code example. It shows that it shows how this is implemented in PyTorch. So first, we need to initialize our model, define a loss function, and choose an optimizer. So here, the loss function is cross entropy for classification, and the optimizer here is SGD, which stands for stochastic gradient descent. So then for each epoch, which is a complete path through our dataset, we need to generate the predictions with the forward pass, which is specified here, and we need to calculate the loss by comparing the prediction to the targets or the ground truth, and we need to clear any previous gradient with gradient.zeroGrad. And then we need to compute the gradients with loss.backward method. And in the end, we need to update the weights with optimizer.step. So basically everything is wrapped up very nicely in an object-oriented manner. So everything here is kind of like object-oriented. You can do this using an object.method for pretty much everything here, as long as you have correctly specified which optimizers you're using, which laws you're using, and how you process your data. So this process repeats for multiple epochs, and it will gradually improve the model's performance as the weights are adjusted to minimize the loss function. So it makes a lot of, so it's very important to define the loss function here. And we got different types of loss function for different tasks. And for classification, we're most likely to be using cross entropy, and we're gonna use other types of laws like mean squared error for regression and something like that. And in here, we're gonna talk about overfitting and regularization. So as we train the neural networks, we often encounter a problem called overfitting, where the model performs very well on the training data, but poorly on new unseen data. So this happens because the model starts to memorize the training examples rather than learning generalizable patterns. So to come back to overfitting, we need to use various regularization techniques. So what we want to do is that we want the parameters to learn the pattern, the overall pattern of the training data without going into the specifics of the training data. So that is what we want. So to combat overfitting, there are a couple of ways we can do it. So the first one is dropout, which is basically randomly disassembling neurons during training. So this will force the neural network to learn redundant representations and not rely too heavily on any single neuron. So it's like training an ensemble of networks and average their results. And weight decay. So weight decay penalizes large weight values in the loss function. This will encourage the network to use smaller weights, which typically leads to smoother and more generalizable functions. And we can also do early stopping. So early stopping monitors performance on a validation set and stops training when the performance starts to degrade. So that will prevent the model from overfitting. And the last one, we can use data augmentation. So this is a very popular approach, even for very recent work in large language models. So it basically saying that we want to artificially increase the training data variety by applying transformations like rotation and flips to existing examples. So basically, we want to make twists to the training examples, and while still maintaining the legitimacy of the training examples, and that will give us more high quality training examples, without um, without forcing the model to memorize the instances of the training data. So the code example here shows how to implement the dropout in a neural network architecture and how to add weight decay to the optimizer. So these simple additions can a lot of times dramatically improve a model's ability to generalize to new data. So an overfitting is like pretty much like tax and death. It is unavoidable. So we have to know what overfitting is and the ways to um, I'm not going to say prevent this issue, but alleviate this issue, solve the issue, resolve this issue. So we can use dropout, weight decay, early stopping, and data augmentation to for regularization. And we also need to know how to define how to access the data, and we also need to be able to handle batching, shuffling, and parallel loading. So working with data efficiency is crucial in deep learning. So PyTorch provides two main tools for data handling. So dataset and data loader. So these are two classes, right? These are two classes that PyTorch provides. We don't have to build them again. So these are already provided. The dataset class defines how to access your data, whether it's stored in memory, in files, or need to be generated on the fly. A custom dataset implementation needs three methods. So we need the initialization method, the init method, we need the length method, and we need get item method. So the init method sets up the access to your data. The length is basically returning the total number of samples in the dataset, and get item function will return a single sample given an index. So if you give it an index and give it the dataset, it will give you the piece of data corresponding to that index. So data loader handles the heavy lifting of batching, shuffling, and parallel data loading. So here is the data loader. The code example shows that a custom dataset implementation that simply wraps existing data and labels. The data loader then creates batches from this dataset, shuffling the data for each epoch to prevent the model from learning the order of examples. So we don't want the performance of the model to be dependent on in which order we feed the data to the model. So the training loop with batches process data in chunks rather than one example at a time. So when we're looking at the architecture of the model, it looks like it processes one example, but in practice, we're giving it a batch of examples at one time. So this will significantly speed up the training. So this structure scales well from small experiments to massive dataset that don't fit in memory. So here is let's put everything together by implementing a linear regression in PyTorch. And this simple example demonstrates the complete workflow from data generation to model training. So first, okay, make it bigger. So first, we generate synthetic data with a known relationship. We generate synthetic data with a known relationship y equals to x plus 1. So this is the synthetic data that we created with some added noise, and the noise is added from normal distribution. While we know the true relationship, we will let the model discover it from the data. So our linear regression model class is minimal. It's just one linear layer that maps from one input feature to one output prediction. So despite this simplicity, it follows the same pattern we will use for more complex models. So the training loop will follow the standard pattern. First, we need a forward pass to generate the predictions, and then we need to calculate the loss. And here the loss is defined as the mean squared error for a regression task. And then after computing the loss, we need to compute the gradients. And in the last step, we need to update the weights using optimizer.step. So after training, we can extract the learned weight and bias parameters, which should be close to the true value of 2 and 1 that we use to generate the data. So this example, while simple, demonstrates all of the key components of the PyTorch workflow. As we move to more complex examples, the structure remains the same, and only the network architecture and perhaps the loss function will actually change. So when you read a lot of academic papers in deep learning, you'll see that a lot of the papers they don't change a lot. They don't change um, a lot of the skeleton code here. They just change the loss function, and then they can make a new paper out of it. Um, so so basically, even when we're working with much more complex models, the overall structure will remain pretty similar. So here we're going to talk about the exercise that we'll need to do for exercise 1, and the link of the exercise will be posted in the description. So we need to put our knowledge in practice with these exercises designed to reinforce the concepts we have covered. So in the first exercise, we'll need to ask you to create a function that normalizes a tensor by its mean and standard deviation. In the second example, we'll need to implement a function to compute the derivative of a cubic polynomial at different points using autograph. And in the third exercise, we need to build a 3-layer neural network for the moon's dataset from scikit-learn. In the last exercise, we'll need to implement multivariate linear regression model on the California housing dataset. So we'll talk more about these exercises in the next video, and you'll be able to find the resources in the description. So congratulations on completing the first phase of the deep learning journey. By now, you should have a solid understanding of PyTorch, automatic differentiation, building neural networks with the NN module, the complete training process, and the techniques to improve generalization. So with these fundamentals in place, you're ready to explore more specialized architectures and tasks in phase 2.